All right. Good morning, everyone. Good to see you again. So today we're going to talk about computational learning theory. Okay, so this is an area that studies some of the theoretical underpinnings of algorithms that has been invented in the machine learning field. And the main purpose of such an analysis is not to basically achieve an exact computation of, say, how much risk you are going to have, how many samples you are going to need to train a model down to certain, error rates and so forth. But it's to really help people establish a connection between a few key tuning knobs in the learning algorithms so that people can get a sense about how to influence the result by increasing sample or by designing different models. But these kind of analysis are, I wouldn't say qualitative, but they're not exactly quantitative. You will see numbers, symbols, which will be entering the analysis in a big O type of fashion, which means that they are up to some constant or up to some lower terms, right? Okay, so one of the key issues about machine learning is actually something known as the generalizability of learning. Say you're training a hypothesis, which gives you an error, right? So remember, this error of the hypothesis is usually, computed on your training data set S, right, which is the data you actually know, the labels and all that. Then you usually minimize the error on the training. And then you need to apply this H hypothesis to some new data. The new data may be coming from the same distribution from which your training data are coming from, but also they can be coming from a different distribution, right? Or maybe a distribution that is not captured so nicely by the training data. And then you want to ask how much risk I'm going to have, how good this particular hypothesis is, even though they are learned only from training data, right? So this is the core of generalizability of machine learning. So today we are going to introduce a few techniques that helps you to analyze behaviors of this kind. Two of the main aspects of core interest, in describing generalizability is the notion of cost. Right here, there are two particular axes of the cost that is particularly interesting. One is known as the information cost. The other is known as the computational cost. So information cost or information complexity is to do with how much training data you need to prepare to train a good algorithm, and also how fast you can learn, say how many iterations, right? You can get to a convergence. Right? This is in the space of, in the aspect of information complexity. And the other is the computational complexity, how much cost you have to pay, in learning from every one example, right? So we're going to see, how these numbers can be connected to the accuracy you are going to achieve on testing the data. Okay, so here is a general kind of a framework that we're going to use to establish this connection. We're going to introduce more formally sample complexity, and we're going to also capture computational complexity. And I want to have a theory that builds the connection between the following things, right? One is about the training examples. For example, the quantity of training example, we call it M. This is basically a notion of the sample complexity. We also want to establish the concept about the complexity of the hypothesis or concept space. That actually has something to do with the cost of learning, the computational cost of learning, because you may design a hypothesis which has a certain dimension, which requires a certain number of features, say 10 features or 100 features. That certainly will affect, the computational cost of computing such hypothesis. And also, it gives you a notion about how much it takes you to exhaust all the possibilities in such space, right? And then we're going to introduce two probabilities, that connects to the notion of accuracy. One is the accuracy of approximating the target, basically the error you're going to make, on the training or on the testing example. And also the probability of successfully attain that training error, say it's small, then what is the probability of achieving that? So remember, there are two types of a probability. One is the probability of making an error, and the other is the probability of attaining a hypothesis that makes small probability on error, right? So this is a double hedging story. And our conclusion will always be presented in the form of a big O notion, which basically means that whatever relationship we are going to present here is usually up to a constant or some lower order terms. So it's not going to be precise, exact. Okay. So let's first get a sense about the H, the capital H, which is the hypothesis space and also the hypothesis. So here is an example of such hypothesis space. It begins with the task of learning, okay? Because a different task, say regression or classification or multitask learning, will definitely, leads you to different hypotheses, and therefore there is space. So here, let's use example. The simplest one, say a binary classification. We've learned a number of different binary classifiers, right? Support vector machines, logistic regressions, and so forth, right? And here, let's imagine maybe the simplest scenario where we can even visualize or quantify the hypothesis space. Say our example X is just a finite list of discrete features. Say here I have 6 features to describe, say, the possible days. Okay, say the sky being cloudy or sun, and the air temperature, humidity, wind, water, and forecast. So let's say we have the 6-dimensional feature for a day. And then our target function is to enjoy or not sports. Okay, so this is basically a binary classification. Given every day, I predict whether you are going to enjoy sports or not, right? Therefore, the hypothesis space, in this case, is just a conjunction of literals, right? You are going to list all these, discrete features, plus the outcome of that. And you can imagine there are all possible ways of combinations of a different feature value. And that leads to a particular way of writing down the hypothesis. And you probably imagine that you can even count the number of possible combinations, such a space could offer, right? So that's leading to the size of the hypothesis space. One of them or some of them may be good enough for you to make a predictive model. And then we're going to train our S, okay? We're going to train the H by training examples S, which is usually, a finite number of feature and outcome pairs. So we've known that already, right? And then we're going to determine, the following things. First of all, we're going to find a H, which we believe to be good on the training set S. And we call it empirical risk minimization in a second. But that's not our goal, because we want to use this for our, testing examples. Therefore, we need to also characterize how good this H is, on all data come from some distribution D. Okay, so that's kind of the whole setup of our analysis. And just depending on how the H look like, we already will be landing on two analytic paradigms. One is known as the PAC-Learning framework. Okay, in here, we basically are assuming that in the hypothesis H, there exists some little h which allow you to perfectly distinguish training examples. Basically, the sample labels is going to be consistent with at least some of the h. Okay, and that means you are going to make a zero error by one of the little h in the hypothesis space, and then the generation error on the testing data is going to be 0 plus something, right? Because you make 0 already on training. Then if you are going to make more errors, it has to be coming from other sources. So we're going to basically, find the absolute upper bound of this error. So it is absolute because the training error is 0. The other framework is known as the agnostic framework. Here, things becomes a little bit more complicated. You have no prior restriction on the sample labels. Basically, you are going to label the sample in any arbitrary way. It could be even wrong labels, okay? But the result is that your hypothesis H, okay, may not contain a little h that perfectly, label the training examples. Okay, therefore, you are going to make a mistake, however you try, on the training data. And then your generation error will have to be additional error on top of the training error you already made. So it's going to be a relative kind of statement of the generation error. So these are the two frameworks we're going to study today. Okay, and in both cases, H, the size of H is finite. We're going to study infinite H in our next lecture. Okay, so the next notion is sample complexity. I just said it already, that it's, in the most intuitive case, it's the number of training examples that you need to learn a target concept up to satisfaction, right? And in obtaining the M, there are multiple scenarios. You can imagine that you may be in a scenario where, and as a learner, you are going to propose an instance that is unlabeled, and you ask a trainer to label. Okay, or you will be dumped by the trainer just a batch of examples which are already labeled that you, as a learner, do not have the right to refute any of the examples or suggest the new examples. Right? And sometimes it could be also a random source that the samples are generated just randomly from nature, and then the teacher provides that. So all this actually also creates different type of risk and guarantees. So in the two frameworks that I'm going to talk about today, the PAC framework and also the agnostic framework, we're going to put a screen here, and we make no distinction along these scenarios. We just basically say that we have examples, okay, as a training data set. Okay, we are going to ignore, for now, the implications of these different scenarios. That makes the problem a little bit easy to analyze. Okay, so here is the protocol. It's going to be very kind of standardized. We are going to begin with the set of examples called H. Okay, and we're going to assume there is a fixed distribution of the data, which is unknown to us, by the way. And then the hypothesis is H, which we have a ability to define, and also the target concepts, say binary label or multi-way label and so forth, which is provided already, by the teacher or by the trainer. And then the learner will observe this set. Okay, the set is labeled, but more importantly, we assume that the examples in the data set, in the training set, also come from that true distribution. Even though we don't know what the distribution is, we assume that the data come from that distribution. Therefore, the training and also the future testing data are following the same distribution. So this is a very important simplification which allow the analysis to carry out in a more straightforwardly. Okay, and of course, the labels also come from the space of all possible concepts. Okay, we are of course we don't actually know the labeling function based on what the label was generated. We just know the label outcome. And our goal is to learn a hypothesis which becomes the estimator of the C function. Okay. Okay. So and for now, in the PAC learning, when we say that PAC learning is about a hypothesis space where there exists hypotheses that perfectly observe or respect the label in the training data set. That basically means that these two are equivalent. The set of concepts is the same as our concept of hypothesis, or the set of hypotheses. Okay, and then the data basically in this case is called noise free. Okay, so now let's look at the error more closely. We already know that there is a term called the training error, which is defined explicitly in this equation. Okay, it's epsilon hat subscript s over h, which is the probability of your predicted label by h disagree with the given label cx. Okay, and empirically this probability can be estimated by a sample average. Okay, that's why it's a hat. It is estimated from your training set. And this is an error that you actually can compute after you train your instance, right? Train your hypothesis. And your goal, of course, is to establish a connection of this training error, empirical training error, on to the true errors, which is defining here. The true errors is the probability of any data coming from that distribution where the prediction and the true label are different. Okay, so how these two connect to each other. And our guess is that they should be very close, because otherwise it doesn't make any sense for us to train a hypothesis and use it for new data, right? But how can we assure us that it is indeed very close, and how close they are? Okay. So graphically, you can see that it is not necessarily automatically guaranteed that they are close. You have a instance of the X where data can be labeled in all different ways. And the hypothesis space basically is probably just a subset of the way data can be labeled. And the training labels C, or the true labels C, okay, is unknown to you in terms of the function. And you only see the instances. But the function probably is another subset of the ways how data can be labeled. And in the event that they are not identical, then there are disagreements, right? And that's basically, a characterization. The volume of these disagreements is basically corresponding to the generation error we're going to have. Okay, so now let's look into how we can kind of put some more explicit quantities and analysis on this error. We're going to use a few very famous probability properties or theorems to prove certain property. So here I'm going to introduce two very important lemmas. Okay, one is called the union bound. It basically characterizes the probability of certain event happen. Okay, and by basically some simple notion of individual probabilities of every event. So this statement says that the probability of at least one of the event out of k events happening is going to be upper bounded by the sum of the probability of each event happening. Okay, so it's a kind of already intuitive. We're not going to prove it. Okay, it's also known as the Boolean theory. Okay, so this basically allows you to establish a connection of a complex event happening within a set versus individual events happening, with certain probabilities. Okay. The other very important lemma is known as the Hoeffding inequality. It is also very important. It is often used to characterize the quality of a estimate of a Bernoulli rate or a discrete, the probability of a discrete event. Okay. So imagine you have a binary event, which say a coin tossing, or a classification error of binary outcomes. And it is having a probability of phi, for example. Okay. And this event is a Bernoulli event. And this true phi may be unknown to you, but after you toss a few coins or after you try a binary classifier on some examples, you can compute basically the probability of account basically the outcome of the binary events. And then that allows you to compute a sample estimation of the phi. Okay. So the Hoeffding inequality tells you the following property. It says that the probability of the sample estimation of this random variable of this rate, which is the mean of the binary random variable, is going to be close to the true rate, okay, with a high probability. Okay. Or in other way, you say the differences of the estimate and the true value to be greater than some small number gamma will be upper bounded by a small number. Okay, the number being exponential of -2 times the error to the square, and also very importantly times the number of examples. So if you read this term, you can see that it's kind of intuitive. The more the m is, okay, the more example you have, then the smaller number this entire term is, right? Therefore, that means if you estimate your rate from more examples, then the probability of deviating from the true value will be smaller and smaller. Okay, so that's kind of the gist behind the Hoeffding inequality. So I'm going to use these two theorems, lemmas down the road to prove some of the learning, properties we're going to look into. Just remember this for now. Now, another concept which helps us to further quantify different hypotheses. I mentioned that there is a H hypothesis space, and there are many little h inside it, but not all of them are equal. There are some h which is making no error, right? Like this. And imagine that there are several such h. Okay, in the entire space of capital H, there is a subset where there lives the h, the little h, which is what we call consistent. Okay, consistent means that they make no error on the training example, and we call this the version space, okay, of the h. So this guy is the version space, which is defined in here. They only correspond to those consistent hypotheses. And you can see the version space is defined very carefully with two notions. One is the capital H, which is the entirety, the universe of that particular type of hypothesis, like this little square. And then the S, which is the training set, which defines this, grounds this consistency. Consistency with what? With the labels in the training set. Okay. So this is known as the version space. And that basically allows us to look into a subset of the H from which we are going to take maybe one of them to be used as our generalizing hypothesis. Okay, so consistent learner is basically an algorithm or an effort which allow you to pick out those little h that is in the version space. Okay. Of course, now we need to know how such hypothesis can generalize. And how they generalize is, with usually people say, oh, they make very little error and they have a high chance of being successful and so forth, right? So here we want to tighten the statement a little bit so that they become really very rigorous, right? And that's what the PAC-Learning framework is trying to achieve. Basically, it says that the PAC learner aims to produce hypothesis H hat. Okay, hat means that it's empirically estimated from the sample, which is approximately correct. What does approximately correct mean? It means that the error of such a H on the true data distribution is close to 0. Okay, and then not only approximately correct, but also achieving this this high mark with a high probability. You can say that, yeah, if I train 100 times of the hypothesis, one of them will be having a very low error, but that's not very helpful because even though such a low error hypothesis exists in the H, you need to train 100 different H to achieve such one. That's no good, right? You want to actually have a high probability of attaining this, right? So this is a double hedging story called approximately probable correct. Okay, so that's what the PAC-Learning is basically trying to state. Probably approximately correct. All right. Now getting a little bit further, we knew that the H, we are going to get is from the version space. They make 0 errors, on the testing data, on the training data. And we knew that they are going to make some error on the training data. And therefore, we need to put a cap on the training error to force it to be small, right? So that leads to the notion of how to exhaust our version space. Okay. So again, here I redraw the graph. This big square is the whole space of H. And this little shape in the middle is our version space. Right, version space, you can see that there are, all the R's become 0. But then, out of this different, 0 error hypothesis on training data, they can still have different values of the testing error, one being 0.1, one being 0.2, and obviously we prefer the little ones. Okay, therefore we're going to now really put a upper bound, okay, of the possible, errors that the hypothesis can be made, okay, and that's basically a technique to qualify basically the version space, or we know as exhausting the version space. How good the version space is. Do they contain a lot of hypotheses which have a large error? In that case, we may want to choose a different H so that their version space behave better, right? But if the version space, has a very small, true error bound, then we're going to basically hope that, one of them, will be very good. Okay, so here is an important statement, which was discovered a long time ago by David Hausler. So it says that you can start by building or identifying a version space with respect to H and S. And you can characterize whether it is epsilon exhausted or not by manipulating the numbers of M and also some other kind of quantities to establish this connection. Okay. Basically, it says that it is going to the probability of a version space to be not epsilon exhausted, okay, can be upper bounded by a quantity in here. Okay, and that's actually very good, because now you know that there is a probability, upper bound of the probability of things not go well. Obviously, we want a version space to be epsilon exhausted, so that we know that every hypothesis inside the version space will have a true error smaller than that epsilon. But if it is not, then we want this probability to be very small, right? So here, this statement basically says that such an upper bound exists. Okay, it is basically bounded by this quantity. And the beauty of this is that now you can have a control, because this M is the number of training examples, right? You can achieve, a very small upper bound of this bad event, okay, just by adding more examples. Right? Of course, you can also make the relaxation of making the epsilon to be very relaxed. That will also make your bad event not happening so often, but that's not very helpful, because after all, you want the theta to be epsilon to be very small, right? So therefore, the thing that you need to manipulate is M. The other thing, of course, is this one. This size of the hypothesis space is another thing that you could make some impact. We are going to discuss that in the next lecture, which amounts to how to do what we know as a structure risk minimization, where by choosing different hypothesis function at hypothesis space, say be it a curve or be it a line, you actually also could have a way to bound such bad probabilities. Okay. All right, so this is a statement. I'm going to try my luck to present a simple proof, so that you also get a flavor about how people in the computational learning theory, use basic statements and properties in probability to establish these kind of guarantees on error. Okay, so this is a cool exercise. Many people are not comfortable with this level of proof, but I'm not going to do it very often. I think today, at the end of the semester already, I'm going to try a proof so that you can see how it was carried out. Right. So we begin from a few kind of conditions. One is that it is not epsilon exhausted. That's one important character, meaning that the probability, of a certain bad event will be greater than epsilon, right? Rather than bounded by epsilon. And the other is the version space, where we have consistent learners, because we're going to only care about the hypothesis in the version space. So consistent learner, meaning that h of x is going to be equal to c of x. So this is a good event. Right? Then we basically want to characterize, say, how basically likely that the h in here is going to be not able to upper bound it in terms of their true error by the epsilon. Okay, so here let's look at all these events very in a sequence. So we are going to have a true error epsilon, which we now assume that it's going to be violated. Now, if the hypothesis has if we have a hypothesis which has a error, a true error of epsilon, then what is the probability of h disagree with the label? Okay, and the xi in the training data x. Okay, and the true error greater than epsilon. So what is the probability of this event? By the way, this event didn't happen. Remember that. This, let me say, call this event AA. Okay, so if A did not happen, okay, that's very important to know because we are really getting the hypothesis from a consistent version space. But let's just look at the probability of what if it happens. What's the likelihood? What is that? Someone want to speak out? The probability of a consistent hypothesis, okay, making an error in the training set, given that the version space is not epsilon exhausted. Okay, I'm going to suggest that it is going to be some number greater than epsilon, right? Basically, epsilon is just the upper bound of all the errors that you could commit by any hypothesis, and the H is just one of these hypotheses, right? Therefore, it will be bigger than that. But remember, this event didn't happen. Okay, what happened is that we actually have something where Hi actually equals to, right? Given that, so this is what happened. So what is the probability of this happens? Do I see anybody charting or what? Right, I saw someone answer already. It will be smaller than 1 minus epsilon, right? Okay, that's nice. And you can imagine that we really want this probability to be big, right? So that it will honor our, because this is happened, this A complement happened. Because we see it happened, it must have a good probability. Otherwise, we wouldn't see it happening, right? Okay, now let's look more. How many examples we have in the training set? Here we have only one event, right? And how about for all the i's? So
Eric, there's a question in the chat. Someone says, is this epsilon the same as the delta we defined initially?
No, it's not. The delta is the probability of getting such a hypothesis, and the epsilon is the error of such hypothesis commit. Okay. Yeah, you can go back and listen, digest very, very deeply about this double hedging story. Okay, one is the property of that hypothesis, achieving a certain error probability, and the other is more on the learner side, how likely I'm going to achieve that particular learner's performance. Okay, so it's not delta. You will see delta very soon. It will actually be in the picture. Okay, so now we're asking the probability of H of xi equals to C of xi for all the i's in S. And given that the whole thing is not epsilon exhaustive. Okay, so what's the probability of that? This is the probability of one event. This is the probability of, say, M event. Well, here someone is suggesting a union bound. I'm not saying at least some or one of the correct label happens. I'm literally saying that all labels are correct, right? Yes, okay, I got the answer. Thank you. It should be 1 minus epsilon to the power of m, because it is a joint probability of all such event happens, right? And you can imagine that it is a number that is, close to 1, right? Okay, so you can basically, approximate this with a exponential. Okay, so this is just by Taylor expansion and a algebra. You can actually write it down in exponential form. Okay. All right. So now we basically, have maybe we can say it the following way. Basically, for a particular h, right, we have a consistent h. It's consistent, and we basically say that this happens with a probability upper bounded by e to the minus m and epsilon. This is one hypothesis, remember. Okay, one hypothesis being consistent. Too bad, I'm losing all the pages. That's okay. Let's just write it from here. So now we have H being in the version space of H and S. Okay, the probability of this, given that the version space is not epsilon exhausted, is going to be upper bounded by this quantity, e to the m and epsilon. Okay, remember that to achieve this, we multiplied m times that single event probability, but this is now a bigger event, on H as a hypothesis being consistent with all the training examples. Okay, now our last point, we are talking about existence of H in capital H. Okay. Basically, we're saying that for a capital H hypothesis, there should be, let's call this event E. Okay, let's call this event E. We need to say that at least one of the events, this will happen, in all the hypotheses in H. Maybe I should say, what is the probability of E of H1 union E of H2 okay. So what is this probability? This is the probability of at least one of the hypothesis in H being consistent.
I have a question. Can I ask?
Yes, please.
The version space is defined as the subset of hypotheses that are consistent with all training examples in S, right? So wouldn't the probability of each hypothesis being consistent be 1?
Well, you see it, but it's we're not talking about a probability, based on. You are talking about an event. I'm talking about the probability of an event. That's different things, right? You could have a version space where all the hypotheses are consistent. That's an event. But what's the likelihood of having such a version space? Right. So we're talking about different things. Okay, yeah. All right, so can someone help with this? This is the probability of having at least one of the functions in the version space to be consistent. There may be multiple, there may be all of that. That's all possible, right? How to characterize this probability? That's where the unity bound is, yes. So you are going to now upper bound this basically by the sum of the probability of every event, right? I equals to 1 plus 2k. And that basically becomes the sum of E, right? And we use the volume of the H to represent the sum. Okay, so that's how the proof is established. Maybe I should flip to the next page. You can see where we are arriving. Some reason this tape. Yeah, okay. So what we see just now being proven is basically this property. Okay, it's the Hausler's very famous PAC-Learning bound. Okay, it basically says that the probability that the version space is not epsilon exhausted after m training example, is small. Okay, it's upper bounded by this quantity, the volume of the hypothesis space times e to the minus epsilon and m. And let's say that we want this to happen, with a small probability delta. Okay, so that's basically delta gets in. Okay, so you can see these are two arrows. Delta is the probability of this event, okay, being happening, and epsilon is just the probability of a hypothesis committing an error. Okay, so these are two things. And to achieve a hypothesis which makes a small epsilon, and to achieve that with high probability 1 minus delta, you basically can connect the epsilon, the delta, and also the size of the hypothesis space with this equation. You need to have m examples greater than this quantity, okay, to achieve an effect that you have a training error 0, meaning getting one hypothesis in the version space, and they're going to have a small epsilon with a high probability. Okay. Are you with me? Okay. Maybe the other way to say that is that, this what's the complement of this event? Here, basically, we say that there exists some hypothesis which is not epsilon exhaustive. The converse of that is that there does not exist any of such hypothesis that is greater than epsilon error, right? And you want that probably to be very high, and that's basically 1 minus this. That means, in the version space, you are very unlikely to get a H that is committing big error or the error greater than epsilon. Okay. Yes. Yeah. Some people asking, so error exhausted is equivalent to no training error, but testing error greater than some error. Yes. So yeah, we're using this basically to establish now a notion of the ED, okay, of H. Okay, and here we basically say that the ED is upper bounded by the epsilon. Okay, because on the training data you have only 0 error, therefore you cannot really claim any error, on the training data set to directly extrapolate. All right, so let's move a little faster. This will take longer than I expect to explain, but let's do some exercise to see how they actually play out in your real training task. Let's say that we're going to learn some simple hypothesis. Say the good day or bad day classification example we mentioned earlier. It is basically the hypothesis was a bunch of Boolean attributes, right? You can imagine that maybe they are three-way Boolean literals, yes and no and don't care. Okay, and then the number of hypotheses for such a attribute function is basically 3 to the power of n being the number of Boolean literals, right? And then you can use this equation, this theorem, to conclude that you need to have the m greater than this quantity to achieve a generation error no greater than epsilon with high probability 1 minus delta. Okay. You can plug in the numbers, in fact. I remember that in our enjoy sports example, we have 6 Boolean literals, and therefore your hypothesis base is 3 to the power of 6, plug in. And you can also say, I want to, with probability 0.95, to attain such a classifier. Therefore, delta is 0.05. And the epsilon, the generated error of the classifier should be less than 0.1%, 10%. Okay, so plugging all these numbers, you roughly can conclude that you need about 100 examples, okay, to define a version space. So this is kind of intuitive, right? The version space is a function of the hypothesis and also a function of the number of examples. If you just use, say, 1 example or 2 examples as a training, you can define a version space pretty easily. Basically, it's very easy to obtain a hypothesis which is correct, making 0 error on the 2 examples. But you can imagine that it would do very bad with a very high probability of doing bad, on the training, right? And here you are going to increase the m so that they have enough examples. If you don't commit any error on enough examples, then you will have a high probability of achieving a good classifier, making low errors on testing examples. Okay. Okay, so this is basically the core of PAC learnability. Okay, a learning algorithm is PAC learnable if it requires no more than polynomial computation per training example and no more than polynomial number of examples to achieve a good outcome with high probability. This polynomial is basically what justifies or qualifies a PAC learnability. And where do you see polynomial? Well, it's because you have this equation. Okay, you can actually compute how many number of examples you actually need to achieve a good result. And in the previous case, you probably can already plug in, for example, in here, h, if it is exponential, some quantity, to the power of n, for example, and then log of that gets n out. Therefore, the number of examples is polynomial to the number of dimensions of the hypothesis. Right, so that is a PAC learnable hypothesis. And also the polynomial is not only to the size of the feature, it should also be polynomial to the size of the C, which is the number of ways you can label, and also 1 over epsilon and 1 over delta. Okay. And here, of course, we see even better outcome. It's the logarithm of 1 of it. That's actually even a better number, in terms of qualifying the M. All right, so I'm done with the PAC learning, which is the basis of all the computational learning theory we later developed for more advanced algorithms and more advanced hypothesis space and more advanced data distribution. So are we still on track? Any additional questions before I move on to the next scenarios? Okay. I'm going to move a little faster on the more challenging scenario of agnostic learning. So in agnostic learning, we are going to basically drop the assumption of C, the labeling function, being within the hypothesis space. That means that if you use a hypothesis inside H, they may make mistakes, right? And we actually will show that in this case, the computational complexity or the sample complexity will be characterized by a different bound, okay, which is different from the PAC learning. In here, you can see there is a epsilon of the sigma, and there are a few other notions that you will see. Okay, we're going to use the Hoeffding bound to define to actually prove this new property. Okay, so a few new concepts. When you have a hypothesis where there does not exist a version space, say I have the H, there isn't a version space anymore, then how are you going to choose a hypothesis, right? With the version space, you choose hypothesis from the version space, which means that they make 0 errors. And without the version space, meaning that there are either mislabel or unaccommodatable label C, what you do could be to adopt this strategy. You're going to just minimize, the error on training example. This is known as the empirical risk minimization. That's very intuitive, right? You just if you don't have a 0 error hypothesis, you choose the hypothesis with the least error. Right? So, for example, in our linear classification, you can basically write down a loss function. The loss function could be a square error loss, or logistic loss or other things, and then you're going to find the data which minimizes that, right? So this is called ERM. So ERM will get you an error, which is this, right? What you want is an error, which is this, right? So how these two connects, okay? That's the task. Again, we're going to make the problem a little bit easier to analyze by assuming a finite H. Although you'll probably see that this is not necessarily very popular, because even in regression, we're going to have an infinite H. You're having continuous parameters, right, for the slope and the intersections. It is infinite. But just for the sake of argument, let's make it finite first to make the proof easy. And we're going to give a guarantee on the generalization error of this. H hat is basically the empirical risk minimizer. Okay. And we're going to show that, the empirical, we need to first show that the empirical error of any hypothesis is going to be a reliable estimate of the true error of the hypothesis. Okay, so right, hat is always indicating an empirical nature that you get it from data. No hat means it's the true value that exists, but you don't know. And we're going to say that these two are close. And then secondly, once this is established, we're going to say that this one somehow leads to a nice upper bound of the error for this, which is the, okay. Okay, that's the strategy. The first one is very easy. The misclassification probability. Okay, so classification could be viewed as a Bernoulli event. It's right or wrong with a error probability. Okay, therefore our empirical error of any hypothesis is just the accounting of the classification outcome, right? And now you remember in the Hoeffding, inequality, we basically have a way to bound the deviation of this estimated error versus the true error, right? Just you making the error as a Bernoulli event, then these two things are really equivalent. So we can basically say the following, that the probability of a sample estimation of the classification error close to the true error of this hypothesis, by just a distance greater than gamma will be small. It will be upper bounded by this term. Okay, basically says that having a bad estimator is going to be having small probability if your M, for example, is large enough. Okay, same thing. All right. And then we're going to have the uniform convergence, which is quite useful here. So we are now again, talking about, in the hypothesis space, which contain many hypotheses. Just now we are talking about one hypothesis, and here we have many hypotheses, right? So we can use the unibound to now characterize a upper bound of at least one hypothesis, okay, being very bad. Okay, and using the probability of only one hypothesis being bad. Okay, so we sum together all these, and we know that it is a finite hypothesis space. Therefore, the number of hypotheses is k. By the way, this should be a greater sign. Okay. So that means with small probability, there exists at least one bad hypothesis. Okay, learned from data. But this also means that the converse can be computed, that the probability that there are no bad hypotheses is going to be very high, 1 minus this small number. Okay, meaning that all the hypotheses trained this way is good. Okay, so so in the discussion above, we basically are able to now establish a connection, between the two type of errors. One is the true error, the other is the empirical error for any hypothesis, and then the gamma, which is the bound of the differences, is a function of the number of examples, the size of the hypothesis space, and also the magnitude of the true errors and so forth. Right. So we can plug in those numbers. Let's assume that we want this probability to be very small. Basically, having bad hypothesis, the probability should be very small, smaller than gamma. And then you can compute now how many number of examples M is needed to achieve that. Okay. And that's equivalent to say that with probability at least 1 minus delta, your learned hypothesis will have a small error, which is upper bounded by the gamma. Okay, so this is very neat. Somehow we were able to prove that a empirically trained hypothesis, based on big enough number of examples, is going to have a small error with a high probability. Okay, and in here there is a observation that is key. Here you can say that the dependency of the M on the size of the hypothesis space K is through a logarithm. Okay, so this logarithmic in K is very important. That actually leads you to a notion very close to the PAC learnability, that a polynomial dependencies, okay, between the number of examples and the difficulty of the problem, or maybe the computation of the problem is going to be honored. why computation is here, because the cost of computing, is very, very deeply related to the size of the example. If you have a example X, which is n-dimensional, let's say, features, then computing a weight function or whatever for the X is usually n steps, right? Because one for each dimension, right? And if this computation is not polynomially related to the M, that's a good thing, because you don't have an explosion of the sample complexity when you want to learn a slightly bigger hypothesis. Say you want to learn a hypothesis with features that is 2 times n, right? Then you are not going to basically get an exponential, say m squared number of examples. You are going to get 2m examples necessary for the learning. That's good. Okay, so the other thing that we can look into is the magnitude of the generation error in addition to the sample capacity. So you can plug in the delta back to the bounds I just had and replace the gamma with this part. And then you can actually see that the differences between this and that can be actually bounded by these quantities. Okay. Now let's see how far that your generation error of a estimated hypothesis can be away from the best possible options you have in your hypothesis space. Because here, is a statement applied to any H. This is for any H inside the H, inside the capital H hypothesis space. But what are the H you actually are interested in at the end of the day? I think there are 2 H's that you're particularly interested in, right? One is the H of hat, which is the empirical risk minimizer on the training data. You basically train a H to the best as you can on the training example, and you get a H out of it. So this, of course, is a member of the capital H. Maybe that's the only thing you worry, but some people also worried about another H, which we call them, say, H star. Okay, H star is this imaginary thing that is also known as the best possible hypothesis in the H. Due to your algorithm, for example, in the EM algorithm that we used to use, you are not always guaranteed to achieve the global optimum, right? You get some kind of estimations. And therefore, your algorithm may not get you to the best possible hypothesis. It's a hypothesis that minimizes your training error in here, but maybe there are even better ones due to many reasons, right? So that defines you basically. So this particular H star defines you the potential of the hypothesis space of H. So we basically want to establish, a bound of what is achieved by empirical risk minimizer versus what can be achieved, at best, okay, in terms of the error. So that's basically can be shown in this way. So it's basically using a trick of leveraging on this particular, Hoeffding bound of error differences. So we use the bound once in this equation. Okay, so this is the differences of the estimated epsilon versus the true epsilon. Okay, the estimated epsilon is on the data, and the true epsilon is basically the generalization on testing data. And this is, defer by at most gamma. Okay. But, this one, the H hat, is guaranteed to be upper bounded by the best error that you can make, right? So there could be another H hat of star in the version space, in the training data set, that can do even better than your current empirical risk minimizer. And therefore we can plug in this in here. Right, so this is just by definition, because it's the best possible hypothesis. So it's surely better than your empirical risk minimizer. Maybe it's the same, but it couldn't be worse than that. And then remember, this is the epsilon hat, right? Because it is an empirical error. Then from here to here, we use this bound again, okay? So that you can basically bound the empirical risk estimator, with the true risk of the same hypothesis plus a gamma. Therefore, now we have two gammas in here. Okay. Then putting things together, we have this very nice kind of statement, which is that the true error of your empirical risk minimizer, okay, is no worse than 2 gammas away from the true error of the best hypothesis that you can get from the hypothesis space. So what does it mean? It means that practicing empirical risk minimizer is a good idea. Right? It's not too far away from the best you can achieve, even though it is not necessarily achievable, but you can get very close to it. And then the gap, which is 2 lambda, is basically this one, which is under control because you can add more samples, for example. You can also relax your hedge on the probability of attaining that. You can also maybe try different hypothesis space to control the size. But in all this, you can basically make sure that your gamma is under control so that your empirically trained estimator of the hypothesis is not too far away from your ideal hypothesis in that space. Okay, so that's basically what we are trying to achieve today, right? So the PAC learnability and also the agnostic learning framework is really giving you that kind of insight, which characterize, first of all, your error, okay, obtained, from, the training data set, is going to hopefully leads you to a good, hypothesis that generalize to the testing examples with this much additional risk. Okay, that's the first story. Basically means that your algorithm in optimizing the training error makes sense, right? And then it makes sense even better when you have the sample complexity under your control. If you can, use more examples, then you are able to kind of, squash or attain that kind of low error of the hypothesis and the high probability of attaining the good hypothesis. Okay. And here, one of the key notion is the so-called learnability, which is that the M and the hypothesis is related through a logarithm, which ensures PAC learnability or polynomial complexity, meaning that when you are facing different problems or adding increase the volume of the hypothesis space, you're not going to exponentially demanding more examples. You're going to be only linearly increasing examples, which actually is something that people can afford. Okay, so I'm going to stop here. Any more questions from the audience? Okay, so I suggest you guys go home and read today's lecture notes very carefully because it is kind of abstract, and it is sometimes the wording is a little bit awkward, right? You are basically characterizing a bad event to have a small probability, and then you claim that the good event will have high probability. Make sure that you understand this kind of indirect argument, from the probability series. Next time, I'm going to talk about how to get more natural by removing the limit of the size of the H, they become infinite. And then under there, what kind of strategy we can adopt to achieve good outcome with high guarantee. Okay.
Hi,
All
I
right,
have
see
one
you
final
next.
question.
Yeah, please.
So just to understand K in an empirical sense, basically K means the number of unique labels in the training and test data, right?
Not the number of unique labels. Ways of labeling, right? It's the hypothesis, not just the complexity of the labels.
I see. So it's a combination of features.
Yeah,
and labels.
You will actually see that the next time. If you have 3 examples, right? You have 8 different ways of labeling them. The K corresponds to that number rather than every label being just a binary. Say you have 3 examples, it's just a 2-way of label, plus and minus. Right? Because we're talking about the hypothesis space, not about labeling space. These are 2 different spaces.
Got it. Thank you.
Okay. Any other questions? We have another 2 minutes.
Can I quickly ask about the notations here? How do you, what's the differences between like error hat H and error H and error hat H star, like in the previous page?
You bet. Yeah, this is, so let's see. H hat is the empirical risk minimizer, right? We know that. And the H hat star is the best possible hypothesis inside the H. Okay, so best. So usually this one will dominate the other one because it is the best. It doesn't mean that you can achieve it. This one is achievable. Then error, epsilon basically is usually suggesting true error. And epsilon hat is basically the error that you measured on data. Okay, so usually you will put a S here to indicate that you use the S training set to measure the error. And then when argument of H hat put in, it measures the error of that one. If argument of H hat star put in, you measure the other one. It doesn't mean you actually can measure it because we said that the H star isn't necessarily attainable, but you can imagine such a quantity exists. Remember here, we are using the tricks to establish a reference point which we know it exists, but we are not necessarily able to achieve that, right? Yeah.
Yes, thanks.
Okay, good, thanks. All right, we're right on time. Thank you very much. We'll see you on Wednesday.